this is a potential difference. Charges will travel according to their positive or negativeness in a potential difference. So as we can see, the negative charges are moving away from the minus sign, and the positive charges, if there were any, would move away from the plus sign, because likes repel and opposites attract when it comes to charges and electrostatic attraction. So my question to everyone is, what direction would an atom travel if an atom was present in this tube and subject to this potential difference? Could anybody put that in the chat box? I'll just wait for an answer. If you'd like me to repeat the question, you can just type repeat the question and I'll do that as well. I'll just ask these questions throughout the webinar to just test. Yeah, so I've got the right answer from someone. Yeah, and I've got another right answer. Okay, it's okay to get the current has gone in my house. So what I will do is switch on the flashlight. Sorry, but I think I'll just switch off my video. Are you able to still hear and see me clearly? Is that okay?
We can see you. I mean, it's not that clear, but
okay,
we can hear you clear.
Yeah. Okay, that's great. I'll just, I've just switched off my video and I'll continue. Okay, the current is back. Okay, so I've got a lot of the right answers from everyone. And if you got the wrong answer, that's perfectly fine as well. So the correct answer is that the atom wouldn't move because the atom is electrically neutral. Yeah, so many people got the right answer. That's brilliant. So because the number of protons is equal to the number of neutrons, the atom wouldn't move when subjected to a potential difference since it is electrically neutral. Okay, so we'll move on. Oh, sorry about that. So as I demonstrated earlier, to find the number of neutrons which are present in the atom, we subtract the atomic mass number from the atomic number. The atomic mass number gives us the number of neutrons plus the number of protons. The atomic number gives us the number of protons. So subtracting them gives us the number of neutrons. So I'll just test this really quick. So if an atom of iron has atomic mass number 56 and Z is equal to 26, how many neutrons are present in this isotope? Could I get some answers in the chat? Okay, great. Okay, so everybody's given the right answer there. So we'll move on. Yeah, that's brilliant. Yeah. So elements are uniquely identified by their atomic number Z or by the number of electrons in the atom. So if you look at the periodic table, you'll see that all these elements are arranged according to their atomic number. That's because the thermal, chemical, optical, physical properties of the elements, they're heavily dependent on their atomic number Z, as we will also see as we move through the physics curriculum. Many of the elements that you will use in radiology, such as the contrast elements, or even the metals which are used for producing the radiation, their properties are also due to the atomic number Z. So now we go to the concept of a nuclide. So a nucleus which is characterized by both Z and A is called a nuclide. The notation for nuclides is the N stands for the element symbol, A, atomic mass number, Z is the atomic number. So that same isotope that I told you about before, in this notation would be written like this. There's also now we have to discuss the concept of radionuclides and nuclear stability. So I mentioned the term before, but an isotope of an element is an atom with the same number of protons, but a different number of neutrons. So for example, you could have that iron isotope I told you about before. It would have the same number of neutrons, 26, but it might have a few neutrons more. So that's what an isotope is. Now, some combinations of neutrons and protons in the nucleus are unstable. And a nuclide with an unstable nucleus is radioactive, and it is termed a radionuclide. So to understand what makes a nucleus unstable, we have to look at the forces which are at play in the atom. So we have the nucleus, which consists of the protons and the neutrons, and we have the electrons which are orbiting the nucleus. So since the protons are positively charged and the electrons are negatively charged, the electrons are held in place by their attraction to the protons. This is important when we're discussing binding energy later. So I'll just repeat that again. Electrons are held in place by their electrostatic attraction to the protons in the nucleus. Electrostatic attraction is based on charge. Now, within the nucleus itself, what you have is a lot of positive charges in a very small space. Now, since all the protons are positively charged, they repel each other. So there's a force which is trying to break the nucleus apart. Now, what holds the nucleus together is known as the strong nuclear force. So this is just a reiteration of what I just talked about. So when you're talking about the electrostatic forces, the electrons are attracted to the positively charged nucleus. The repulsive force between the protons tries to break the nucleus apart. The neutral neutrons help to separate the protons and reduce the repulsive force between them. So an important thing we have to know about the electrostatic force is that it is heavily dependent on distance. So the closer that you bring two opposite charges, the more that they will try to repel each other. So the presence of the neutrons within the nucleus actually helps to separate the protons and creates a little bit of stability. But the main force which contributes to the stability of the nucleus is the strong nuclear force. Now, this strong nuclear force acts only on neutrons and protons. The strong nuclear force is attractive at very short distances in the range of 10 to the power minus 15 meter, that's a femtometer, and repulsive at distances shorter than that. So this is why the distance between nucleons in the nucleus is usually in the range of 5 into 10 to the power minus 16 meter. That's because this is the distance at which the strong nuclear force is at its most attractive. So that's the most stable configuration for the nucleus to be in. And this is a concept that we'll encounter again and again and again, is that particles and elements and everything in nature seeks stability. So if there's something which is a more stable configuration, they will seek that repeatedly. So what happens to an unstable nucleus? So if a nucleus consists of neutrons and protons which in a configuration that is unstable, what it will do is repeatedly decay into smaller nuclei until these nuclei reach a stable configuration. So a radioactive nucleus will decay until a stable nucleus is formed. Now, for elements up to calcium, for which the atomic number is 20, stable nuclides have equal numbers of neutrons and protons, or they might have one additional proton. So that's what's happening in the periodic table up till atomic number of 20. In the stable nuclei, you will have almost equal numbers of neutrons and protons, or you might have one additional proton. Now, beyond calcium, stable isotopes have more neutrons than protons. This is because as the number of protons increases in the nucleus, the repulsive electrostatic force grows greater and greater, and the extra neutrons will help to stabilize the nucleus further. This concept is important when we discuss radioactive decay. We will be discussing that later in a later webinar. So now we're going to move on to the concept of electron shells, which is very important for understanding the processes which produce X-rays and gamma rays. Now I'm just going to pause the share for a second just to show you that, oh, that's the light gone again. So just stop my share for a second. Yeah, I just want to show you the notes that I prepared for this session. So I might miss something during my presentation. I just wanted to say that there are very detailed notes which are accompanying this. And I think if you go through these along with your other preparation, this will be like very helpful for the preparation that you're doing for the MCQs. And you'll get those notes as well on the revised radiology platform. So moving on to coming back to the concept of electron shells. So if we look at this is a simplified model which we use to understand radiation which happens in the atom. So we consider that the electrons which are present in the atom are present in circular orbits or paths which we call electron shells. Now these paths are fixed. Electrons cannot exist in the atom outside of these paths. These paths are circles which center on the nucleus. They're also at fixed distances from the nucleus. Each of these paths is also associated with an energy. So let me get an answer in the chat right now. So we know that, just where's the chat? There it is. Okay. So we know that the electrons are attracted to the nucleus. So which of the, also the shells are labeled successively as the K shell, the K shell, the L shell, the M shell, and so on, etc. The outermost M shell, or whichever is the shell for the atom in question, is called the valence shell. There are also unoccupied shells beyond that in which the electron can exist. So this is my question for the chat box. In which shell would the electrons be most strongly bound to the atom? Would it be, okay, getting an answer in the chat, that's the K shell. Does everyone agree in which shell would the, okay, so everybody knows the answer. And of course, that's because of the electrostatic attraction with the nucleus. That's great. So I will move on from here. So some more facts about the electron shells. Each shell can hold only a certain number of electrons and no more. The K shell can hold 2 electrons, the L shell can hold 8 electrons, the M shell can hold 18 electrons. And we don't usually discuss, we use elements which have shells beyond that, but I don't think you need to know how many electrons are present in those shells. The electrons in each shell have a specific energy which is determined by the shell. So all the electrons in the K shell have the same energy, all the electrons in the L shell have the same energy, and all the electrons in the M shell have the same energy. And the shell which is closest to the nucleus has the lowest energy. The shells with lowest energy must be filled first. So because the electron, which is in the K shell, is the most strongly bound to the nucleus, the electron itself has the lowest energy. It cannot leave the nucleus easily. So that is the concept. So this helps us understand the next concept, which is binding energy, which is extremely important when we're trying to understand processes which involve radiation. So bound electrons are held in orbit around the nucleus. Free electrons are not held in orbit to any atom. They're free to go anywhere they want, and they have an energy which is expressed by 1/2 mv squared. This is the formula for kinetic energy. So the terms in this equation are E is for energy, m is for the mass of the electron, and v is for the velocity of the electron. So just some important points about binding energy. The binding energy is the amount of energy that the electron needs to escape the electrostatic pull of the nucleus. This energy is equal to the energy released by the electron when it is freed from the nucleus. So if an electron had to be removed from the K shell, for example, it would need to absorb a very specific amount of energy, and that amount of energy is the binding energy. So what factors does the binding energy depend on? This is important. The binding energy depends on the shell from which the electron is removed. So the closer to the nucleus, the greater the binding energy. And this makes sense because if an electron is very close to the nucleus, it's right in the midst of the pull of the protons. So it would need a lot of energy to escape from that. Whereas if it was in the valence shell of the atom, it would be separated from the nucleus by a lot of distance. So it could be freed with comparatively less energy. And the binding energy of an electron also depends on the atomic number of the element. Binding energy increases as the atomic number increases. And can I just ask in the chat why that would be? Why would binding energy increase as the atomic number increases? It's okay if it's the answer is wrong as well. That's totally fine. Protons increase. Yeah, that is exactly the right answer. Okay, so we will move on then. So just a question for the chat box here. Could I get an answer for this question? Okay, yeah. Okay, so everyone knows the answer to this one. That's great. So this is just to put it into numbers, just to drive the point home. For tungsten, the atomic number is 74, and the binding energies of the different shells are EK. So K, the subscript there indicates which shell they're a part of. 70 kilo electron volts, 11 kilo electron volts, and 2 kilo electron volts. So we see very clearly here, the further that you get from the nucleus, the less energy is required to remove the electron from that shell. Now, here's another question. Could I get an answer in the chat? Oh, sorry about that. I'll just wait for an answer to this in the chat box. Just trying to open up the chat box. Yeah. Okay, brilliant. So this is an important table. It's giving us the atomic numbers and K-shell binding energies of some elements which are commonly used in medical imaging. So if you want to take a screenshot of this, that's perfectly fine. Just notice that the binding energy here is expressed in kiloelectron volts. And we see very clearly from this table that as the atomic number increases, so does the K-shell binding energy. So moving on to the next concept. So now we're going to talk about something which is known as the excitation of atoms. So an atom is said to be in its ground or non-energetic state when all the electrons in the atom occupy the lowest energy shells. So we know that the lowest energy shells fill up first. So for example, if there are no vacant spaces in the lowest energy shells, the atom is in its normal state, its natural state, and the word we use is the ground state. Now, if an electron in the atom moves from its usual position to a shell which is higher in energy, then that is said to be the excited state. And we know that to raise the atom to this excited state, the electron has to absorb a specific amount of energy. So this is just showing what might happen. Sorry. So the electron is in its normal position around the nucleus. It absorbs a photon, which gives it the energy that it needs to move itself from the lower energy shell to an excited state. So how can the electron absorb this energy that it needs? It can do this by absorbing energy from thermal vibrations. This is what happens in X-ray production in X-ray tubes. It can do this by interacting with an energetic charge particle. So thermal vibrations, that's what happens on one side of the X-ray tube. Now, electrons making the transition by interacting with energetic charge particles is what happens on the other side of the X-ray tube. It can also do this by absorbing a photon of light, which carries the right amount of energy. So the other process which happens here is that when an electron has moved to, when the atom is in an excited state, that is when there's a vacancy in a lower energy shell, an electron will tend to fall into that vacancy to fill it up. And when an electron falls into the vacancy in a lower shell, it would emit some energy in the form of a photon.